So good afternoon once again, and you are welcome. It's been quite a while since we had a meeting, so I believe the lecture we are making progress, and you are also getting to learn uh, about statistical inference. So make sure you follow the instructions and you also seek for guidance when necessary. Uh, don't wait until the last minute. Make sure you submit the assignment, the quizzes, and everything. They are all being monitored, and they will be graded, and they will count towards the final grade. If you have issues, feel free to let me know. We are here to solve your problems. Problems relating to this course. So before I continue, if there is anything anybody wants to say quickly. If not, then let me share my screen. So you are already familiar with the Google Classroom, and here you have the stream page. Here you can join, always join from here if you have participating for the first time. Take time to come to the class, make announcements, make comments, say something, ask questions, and also answer questions. On the classwork page, you should be able to see the assignments that have been posted. More are coming as we progress in the course. Here you have the quiz assignment. Oh, let me add you. Should have told me, honey. So I will add you now as a co-host. Or are you a co-host already? Honey, yeah. So you are a co-host automatically. So you have so far we've had 2 quiz assignments, so they are still there. I know some people have not submitted this one. Only we still have about 53 who are yet to turn in their own assignment or quiz. Here we still have about 47 who are yet to turn in their assignments. I'm not sure how many people have taken time to watch these videos here, which I think will help you to master statistics properly. So we are in lecture 2, and the lecture material has been posted. I also have the lecture slides. The one I will be using to teach is this one, so you already have it. You can download. So at the end of this lecture, I'm going to post the video and the attendance sheet. The previous lecture, the video is here, so you can also take time to watch it, even including the whiteboard, the Jamboard, so you have it. We could also continue using that board so that it will help us to preserve our discussions. So what do we have today? This is what we have today. So you can see this is the long list of issues we want to talk about. But the main topic is that we want to look at sampling distribution of a statistic. Sampling distribution of a statistic. But before we go into that, let's review the first topic. The first topic focused on the sampling, and I told you what sampling is about. So it's all about selecting a subset from a larger group, which we call the population. The aim, of course, is to understand and to analyze the characteristics of the population. So sometimes it's inevitable. It's not something that you have option. You really don't have option, but to take a subset, to take part of the population. This will allow you to understand the population, particularly if you are dealing with a very large population. So you can easily manage that population by taking a sample. And also, it's cost effective, and you save time if you have to take a sample than dealing with the entire population. So you can also be sure that your data collection will be more accurate. And you can easily have access to fewer cases than when you have to deal with a large number of cases. So there are situations also where handling the entire population is not practicable. So you can easily settle for taking sample. One other thing that one has to consider in taking sample from the population is to ensure representativeness. And I hammered this very well when we are talking about sampling techniques. Some techniques will give equal chance to all members of the population. Some will not give. So ensuring representativeness is very important, because you want your sample to truly reflect the diversity of the population, to reflect every group, every category that constitutes your population has to be represented. And representativeness is critical for accuracy. If you want evidence from your sample to be reliable and useful for statistical inference, which we will talk about later, like hypothesis testing, like constructing confidence interval, and so on like that. Your sample must be representative. Otherwise, your conclusion will be erroneous, will not be valid. So sampling, the approach of drawing sample has application in different fields of study. Market research, public health, social sciences, even in your field, if you are not in statistics. So you take sample to help you take quick decision, and also to have insights about the population. So that's a quick review of lecture 1. But today's lecture, which I consider now to be lecture 2, which is about sampling distribution of a statistic. The objective of this particular lecture include: 1, you must understand what the concept of sampling distribution or sampling distributions are. So why do we need to discuss what do we even mean by sampling distributions? We've talked of sampling. Today we are talking about sampling distribution of a statistic. So we need to know what it means when we talk about sampling distribution. We will also be able to talk about a new concept which is called standard error. So standard error is something we are introducing today, which will come from sampling distribution. We are familiar with the concept of standard deviation, and I remember we discussed that extensively. Here, I talk about when you have population, and then from your population, there are parameters you can calculate, like standard deviation, like variance, like the mean, and then the corresponding sample. We've not talked about standard error, so we will talk about standard error, which will be a new concept in our discussion today. So you will know and be able to distinguish or separate standard error from a standard deviation. Then you will know some properties of sampling distribution, not just of the sample mean. So we will also talk about the sampling distribution of other sample statistics, like variance and proportion. So we will discuss about sampling distributions under some conditions: normality condition, non-normality conditions. How do sampling distributions how do they behave? So this is what we want to talk about. So let's start with some of the things we already know before. You already know about population distribution, key parameters, which are the ones mentioned here. So if you have your population, this is population, and then you have your sample. So earlier I told you any quantity, this is sample. If you measure any quantity, then we will, in the population, we will call that parameter. So quantity like the population mean, like the population variance, like the population standard deviation. The corresponding quantity that you can measure in the sample is the sample mean, which we represent by X bar, is the sample variance, which we represent by S square. It's also the sample standard deviation, which is represented by S. We can also talk about proportion. So we can talk of population proportion. Population proportion. So we will use small p to represent the corresponding sample proportion. So for now, we are dealing with population. So in population, parameters like population mean is represented by mu, and that can be calculated using this expression, which is the sum of all the average of all the values in the population. So, and that is obtained by summing all the observations, dividing them by the number. So the variance, you are familiar with that, which is by squaring the deviation of each observation from the mean, from the population mean. So each observation minus the population mean is called the deviation. When you square it, you have this expression. When you sum up all the squared deviations from the population mean, then you say you have the sum of the squared deviations. When you divide that by n, that gives you the population variance. So what it does is, when you calculate the population variance, it simply captures the average square deviation from the mean. That's the interpretation. So it simply shows on average how each observation departs from the average, from the population mean. The square root of the variance is called the standard deviation, and that's the formula. So it simply indicates the typical distance of the values from the mean. Now we want to talk about the sampling distribution of a statistic. But before we go there, we have said that any quantity you measure in the population is parameter. So any quantity you measure from the sample is called statistic. So if it is only one, let's say sample mean X bar, then it is called statistic, no S. But if you now have two or more, so the plural of statistic is statistics. So get that very well. So so that's where the course takes its word. Statistics is actually talking about what to measure from the sample, quantities that you measure from the sample. So if you measure only the mean, then you are talking about a statistic. If you measure only the sample variance, then you are talking about a statistic, and so on and so forth. So you should be able to differentiate between parameter and statistic. And that takes us to the next issue when we talk about the sampling distribution of a statistic. So which means we will be interested, first of all, in a statistic. And a statistic could be the sample mean, which we call X bar. The statistic could be the sample variance, which we call S squared, which could also be the sample standard deviation, which we call S. It could also be the sample proportion, which we use small p to represent. So each of these is a statistic. We are now going to look at the sampling distribution of this statistic. But the question is, what is sampling distribution? So if you have any question, feel free to ask, raise up your hand, and then let me know. I think we have a good number in the class now, 49, but that's not even up to 1/3 of the expected class size. If you are following me, type yes in the chat menu. If you are following me, type yes in the chat menu. Let me know those who are following me. Some people are following. That's a good one, which means I'm not alone. Oh, wow. So I can see wonderful people like Samuel, Ajayi, Anointing, Ayila, Success, Adebukola. They are all following me. Nobody has said no. Okay, so I'm going to clap for you. That's good. Sultan, yes, you can unmute yourself and talk to me. Sultan, unmute yourself and talk to me. If you are,
Okay.
I can see your hand is up. Sultan, is it an error? Okay. Obioma, you can talk to me. Obioma Ezilsha, your hand is up. Don't waste time. Our time is going. We have a lot to do. Or you can also type your question in the chat menu. So let me go back to what do we mean by sampling distribution? So it's a very simple thing. It simply describes the distribution of a specific statistic. And that statistic could be sample mean. Is
Oh, sir,
somebody
no, don't
talking?
worry. I wanted to say yes, sir, because my phone was overheating. It was not responding properly. So I wanted to, say yes, I do not type you well.
Okay. Okay, Obioma, no problem. But at least you are with me. So if you have any question, then if you type your question, honey, you can just alert me in case there's somebody who has posted the question.
Okay, sir.
Yeah. So let's understand what sampling distribution means. It simply describes the distribution of a specific statistic, and I've given you different statistics that we can have. We can have the sample mean, we can have the sample proportion, we can have the sample variance, we can have the sample standard deviation. So, but how do we get this distribution? So, by the way, you should know what distribution is all about. For when I say distribution, when I say distribution, let's understand that. So, distribution. Let's say in this class, I'm interested in the gender. The first person is female, another is female, this next person is male, female, male, female, female, male, male. How many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's even say we have another one. Now, this is just a data about the gender of 10 students in this class. So I can form a frequency distribution table. So I talk about the frequency distribution table. So in this table, I'm going to have the gender. So I'm going to have the gender and I'm going to have the frequency. So for female, I'm going to say how many? 1, 2, 3, 4, 5, 6. So frequency is 6. For male, I'm going to have 1, 2, 3, 4. So I have male equals to 4. Everything 10. This is what we call distribution. So because it's counting the frequency, that's why we call it a frequency distribution table. So a distribution is like a summary table of any measure that we are interested in. So don't get disturbed by that word distribution. So it is a summary table, so to say. No. So we can have frequency distribution table, cumulative frequency distribution table. We can have all manners of distribution. So it helps us to see the pattern easily in our data. And that takes us now to the next concept, which is distribution of a statistic. So remember that we are taking a statistic, let's say X bar. So if you have a population, maybe I should just go to another page. So if you have in your population, let's say 3 students in the class. So and that constitutes the population of the class. We have 3 students and we are interested in the age of the student, and maybe the age of the first one is 18, another one is 22, another one is 17. So this is the population. This is the population. Let's say I'm interested in sample and I'm taking only 2 samples from this population. So I can take 18 and 22 if I'm not going to do it with replacement. So this sample is going to be drawn without replacement. So I can take 18 and 22. I can also take 18 and 17. Can somebody help me with the other one? I can also take 22 and 17. Is there any other combination that is possible? So from this population, I can call this sample 1. Sample 1. This is sample 1, sample 2, sample 3. So I call this one sample 1. This is sample 2. This is sample 3. One thing that may happen now, suppose I'm interested in a statistic. So I'm interested in a statistic. Sorry. I'm interested in a statistic. And that statistic is the sample mean. Sample mean. In this case, sample mean is X bar. So 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 which means every sample here will have its own mean. So for sample 1, there will be x bar 1, which is the sample mean for sample 1, and that will be 18 plus 22 divided by 2. Who can tell me? Somebody should write that down. Write it in the chat manual. Let me see those who are following me. What's the, 18 plus 22 divided by 2. Who has done it? Somebody got it. Ajayi, thank you. Adebola, you are following me. Can you do the rest? So this is 20. X bar 2. What is that? Who has done it? Who has done it? X bar 2 will be 18 plus 17. That is 35 divided by 2. Has anybody done that? 17.5. Amora, thank you. You are working. You are working 17.5. Then I have x bar 3. X bar 3. That's 22 plus 17. That's 39 divided by 2. Who has done that? That's, 19.5. You are all wonderful. You are all wonderful, 19.5. So which means I have only one population, but you can see I have several samples of the same size. So I have several samples. I have samples of size 2. Of size 2 from this same population. But let's look at, who is that? Let's look at, suppose I'm interested even in the population mean here. I can only have one population mean, which we will call mu. And that will be 18 plus 22 plus 27 divided by 3, because there are 3 of them. 18 plus 22 plus 17. What is the mean of that? 18 plus 22 plus 17 divided by 3. Who has done it? Who has done it? Is it 19? 19, I can see wonderful people. They are working. Olaoluwa, Billy Kiss. Clap for yourself wherever you are. Let me even clap for you from here. Let me clap for you. You are getting it. Benga, Joshua, wonderful. Toby, which one are you calculating? Toby, are you with us? You got, I can see you getting something that is not the same with others. Maybe I'm the one that is wrong. 18 plus 22. Of course, that is 40. So 40 plus 17, that's 57. So 57 divided by 3. So Toby, you are wrong. This should be 19. So maybe I should withdraw my clap. But don't worry, I give you the clap. Sorry. You divided by 2. It should be divided by 3, since we are talking of. So that's good. So this is population mean. Can you see? What point you should know is that when you take sample, suppose somebody decided to take this sample, this will be his own average, which the person will be using to represent this population. If somebody took this sample, the average will be 17.5, and we'll be using this sample to represent this population. So the same thing with this. So one thing we will quickly do now, when we talk about sampling distribution of a statistic. The statistic in question here is the sample mean. So if we are talking of the sampling distribution, then we are now interested in the distribution of the different possible values that statistic will produce at a given sample size. At a given sample size. So let's go back to our note. So that is what the fourth point, describe the distribution of a statistic, of a specific statistic. It could be mean, it could be proportion, calculated from all possible samples of a certain size from a population. Remember, we have taken sample of size 2 to get the first sample, the second sample, the third sample. So the sample size is the same for all the possible samples that we could take. And then the distribution is what we call the sampling distribution of that statistic. So what I've done here now, I can now call it sampling distribution of sample mean. So I'm replacing that word statistic because I've computed for sample mean. So I can now talk of sampling distribution of sample mean. I can also be interested in the variance. Since I have 2 here, instead of finding if my statistic is variance, then I can find the variance of the number. Then I will be talking about sampling distribution of sample variance. So like that, I can have sampling distribution of sample standard deviation. I can have sample distribution of sample proportion. So I can, any statistic, that is any quantity that you compute from the sample, then you can find the sampling distribution of that statistic. All you need to do is to compute that statistics at a given sample size for all possible samples that you can draw from that population. I hope that is okay. If you get it, then type yes in the chat menu. If you get Trisha, good. When I have money, I will send for you. Praise, that's good. Anointing, Oluwafemi, when you just remind me when I have money, I will send money to you. I'm so poor now, so don't worry. Olaoluwa, I can see you. Ogunsanya. Yes, some people are not saying no. Maybe they say yes when they mean to say no. Maybe they say yes when they mean, do not say yes. To say no. Mute yourself, Akinyemi, don't let me mute you. If you are, except you want to talk, that's where you should. Yes, so a good number said yes, so we are good to go. You are following me, that's very important. I'm happy you are following. So let's go back to our note. So what we have noticed is that there is a variation. There is a variation in that statistic that we have computed and in the population value. Population value is 19, but with this sample, we got 20. Population is 19, but with this sample, we got 17.5. Again, with this sample, no, we got 19.5. So there is a variation. That's what the second point is saying. Variation in statistics. Each sample can yield different statistic values leading to variability in result, which we have seen. So that leads to the construction of sampling distribution, which is created by calculating the statistic for every possible sample, which we have done. So we have computed that statistic for all possible samples. There are only 3 possible samples from this population that we have been. So we have computed that statistic for all possible samples. Sometimes all possible samples could be several hundreds or thousands. So we need to compute all of that. And therefore, when we compute that, all possible statistics, we can plot and get the frequency table. We can plot the frequency, and then what we have would then be called the sampling distribution of that statistic. So we can visualize it using histogram, frequency curve, and so on, which you have done in your descriptive statistics. I'm sure you are following. So, but quick concept that you also need to be reminded is the fact that when you take your sample, like I was trying to do, so it could be with replacement, with replacement and without. So let's say, your sampling procedure. One, it could be without replacement. Which means if this is Kemi, if this is Aisha, and if this is Bolu, and I'm supposed to take 2, then if I take Kemi and Aisha as my sample, then before I take another sample, none of these 2 will be replaced. So if I take Kemi, I can only, if I take another sample, I can only take if I take another sample from this, you will know that before I take that sample, I'm not going to replace Kemi and Aisha. So that is without replacement. It means the item, before another round of sample is drawn, the item will not be replaced. So you will have fewer. As you take the sample, you will have fewer. But 3, you can take with replacement. So what that means is that I can, if I take Kemi, Aisha, then before I draw another sample, I have to replace Kemi and Aisha. So which means even the 2 can be sampled again. So when you are dealing with replacement, an item can be selected more than once. An item can be selected more than once. But without replacement, an item cannot be. That's why in our results here, you will realize that I cannot sample 18 2 times, because I pick 18 the first time. So because it's without replacement, so I cannot pick 18 the second time. I can only pick 22 or 27. And I pick 22. I pick 18 the first time. If I now want to pick the second one, again, I can't pick 18. I can only pick 22 or 17, so I pick 17. If I pick 22, again, I can't pick 18 because it's I can't pick 18 because it's no longer there. Or so I can only pick 22 and 17. So this is what happens with replacement. And therefore, here, the number of possible samples when sampling with replacement is given by the formula n raised to power k. But before we do this, let's look at the formula for without replacement. In our own, so n is 3 and 2 is the sample we are taking. So without replacement, you can take, in our case, you have your n, the population size is 3, and you are taking the sample of k, which is 2. So we can only take 3 combination 2. And that's why you have 3 factorial over 2 factorial 3 minus 2 factorial. That's the formula that you see here. So, of course, if you calculate that, that's 3 times 2 times 1. This is 2 times 1 times 1. So you have that. That is 3. And that's why we can only have 3 possible samples. We can only have 3 possible. These are the 3 possible samples that we can have. So then, if it's going to be with replacement, so then this expression will tell us the number of possible samples that we can draw. That is n raised to power k. K is the sample size. So in our case, n is 3 raised to power 2. So you can have 3 raised to power 2. So if we are doubling of with replacement, it's n raised to power k. And this is 3 raised to power 2, which is 3 times 3, which is 9. So if we are taking with replacement, if we are taking this 18, 22, 17, 18, 22, 17, with replacement, then since I'm taking 2 at a time, I can have 18, 18. I can have 18, 22. I can have 18, 17. Then I can have, since I'm taking with replacement, I can have 22. I can have 22, 18. I can have 22, 22. And I can have 22, 17. And then, of course, I can have 17, 18. I can have 17, 22. and I can have 17. So that's how we arrive at 9 possible samples. So you need to get x bar 1, x bar 2, x bar 3, up to x bar 9. So this is with replacement. This is with replacement. Somebody raising up hand? No. So if you follow me up to this point, say yes. If you follow me up to that point, say yes. Yes, I can see Amora, Domi, Ogunsanya. Oh, these people are following me so closely. Esther, have something to say? Following me so close. Esther Degun, do you have something to say? Esther Adegoyin, you have something to say?
Hello everyone. I believe Prof will join us shortly. Okay, he's here. We can't hear you, sir.
No light, and I'm having challenge with my inverter. So I don't know what to do now. So if it stops, then that will be the end of the class. We will have to continue from there next time. Uh, so uh, apology for that, or we can have another schedule to be able to finish up. But I'll communicate to you on that. So we have to stop at this moment because of the light. Or let me switch off the light. Let's see if it will stop. Just a minute. Just a minute. Okay. I think it may be a little bit dark. Let's see how it works out. Okay, I think the class is still there. So we have to manage the situation. So let's continue. Sorry for that break in transmission. Yes. So let me share my screen again. Good. So this is where we had the disconnection. So we were talking about with replacement, and we've talked about without replacement. So those concepts, I think now you understand. Now, so remember the formula for getting the number of possible samples that you can draw with replacement. And then the formula that you can use to determine the possible samples that you can draw without replacement. So let's see what happens. I use computer to do this. So you have a population which I define as 0, 2, 4, 6. The way I define population here to have 18 to 22, 17. So here I also have a population which I define to be 0, 2, 4, 6. It could be 4 students and their scores. It could be 4 students and the amount in their pockets. Maybe naira in their pocket. This person has 0 naira. This has 2 naira. This has 4 naira. This has 6 naira. Or it could be the amount of dollar in their pocket. But there are 4 of them in that population. Now, the second line will generate all possible samples of size 2 from this population. So the first sample is the sample of 0 and 2, 0 and 4, because this is a sample without replacement. Is sample without replacement. So, we are going to have 4 combination 6. Can somebody work that out? 4 combination 6. What is it? 4 combination 6. What is it? What did you get? Put your answer in the chat menu. 4 combination 6. Put your answer in the chat menu. Nobody has typed. For combination 6, yeah, sir, do you mean for combination? How many? What I mean is this: you have how many observations do you have? 1, 2, 3, 4. That's the population size. Your n, and you are taking sample of size 2. So you have n equals to 4, n equals to 4, and you have k equals to 2. So since you are sampling, without replacement, so that is n. You are sampling without replacement. You remember the formula for without replacement is n combination 2. How many of you have generated results? 6. Excellent. 6. So that is going to be 4 combination 2, which is 4 factorial, 2 factorial, 4 minus 2 factorial. So this is 4 times 3 times 2 times 1. And this divided by 2 times 1. 4 minus 2 is 2 times 2 times 1. So you will see that this is equals to 6. Next time, I won't do it for you. Abolaji, Justin, Daniel, Shidera, that's good of you. So let's go back to our discussion now. So that's why we have the first sample is 02, 04, 06, 24, 26, 46. So the system, the computer, the program is able to generate 6 possible samples since they have size 202. So you can find the mean of each sample. 0 plus 2 divided by 2 is 1. 0 plus 4 divided by 2 is 2. 0 plus 6 divided by 2 is 3, and so on like that. So what you have now, they are called the sample means. The sample means. So we can now have the distribution, the frequency of the sample means. So for sample mean 1, it occurs only one time. That's the frequency. The sample mean 2 occurs only one time. Mean 3 appears only 2 times. 4 appears one time, and 5 appears. So this must add up to 6. That is what so when you now plot the histogram, of the sample mean, you can see 3 appears 2 times, others appear 1 time. This is the histogram of the sample mean, right? So so you can also try your hand, you can put as many values here to represent your population, and then try as many as you can. Try as many as you can. Quickly, because my system is still shouting seriously. Then I did a simulation this time to be able to talk about proportion. So in that simulation is about you are tossing a coin I think we have to stop here somehow, if you don't mind. We will continue from here. The inverter is shouting. So sorry for that. Are you okay? Permission to stop here. Say yes. Okay, thank you very
Yes,
much.
sir.
Thank you, thank you. I will. It's unfortunate.
No
It will
problem,
not
sir.
happen again. So
Thank you, sir.
enjoy the rest of your day.
Same
Thank
to
you,
you,
sir.
sir.
Same to you, sir.
Yeah,
Bye, sir.
Take care, sir.
it's like some people are happy.
No, sir. No, sir.
We're not happy, sir.
So I believe I'll be taking on the mantle of the class. So where did we stop, guys? Oh, everyone should jack later.